Okay, so if you've been following generative AI, you know how these incredible images often get made. It's kind of a weird process, right? You take a perfectly good image, wreck it with noise or blur, and then teach the AI to undo that damage. But what if the way we wreck the images wasn't just random or, just a simple blurring? What if corrupting the image felt more like, I don't know, stirring something, swirling, mixing, with actual directions to it? Let's unpack this. Today we're doing a deep dive into some really interesting source material from ICCV 2025. This paper is called Beyond Blur, a fluid perspective on generative diffusion models. And our goal here is to figure out how adding complex dynamics, directional flow, even turbulence help. And also, what are the sort of physical controls they use to get just the right amount of this controlled chaos?
It's a really neat conceptual shift. The new ICCV paper explores the idea of using turbulent advection to improve the generation.
Traditionally, diffusion models like DDPM just add Gaussian noise, right?
Right, that's purely local, pixel by pixel, no special structure.
And in the inverse heat dissipation approach, the images are blurred according to the heat equation.
Yeah, that preserves color intensity, but it's isotropic, like ink spreading evenly in a still water. No swirl, no direction.
So those methods do not have large-scale coherence. This new one brings it back.
Exactly. It uses physics to create anisotropic texture shifts during the forward corruption process, literally treating the image like a fluid being moved around.
If the advection diffusion operator conserves mass, isn't it trivial to reverse?
No, because while nothing is lost, it's scrambled, like mixing paint colors. You can't easily unmix. That's what makes the reverse process non-trivial and forces the network to learn the structure.
How do they model this mathematically?
They use the advection-diffusion reaction equation. The diffusion corresponds to blur its smooth details while conserving the total intensity. The advection is the actual game changer. Here, the external velocity field shifts intensities directionally. It is also conservative. And the reaction term is the classical Gaussian noise injection. It is the only non-conservative part.
So noise isn't the main corruption driver anymore.
Correct. It's just a small nudge for stability. The corruption of information is driven by a dissipative blurring and structured turbulent flow.
But to advect an image, you need a velocity field. How do they generate realistic turbulence?
They used a spectral turbulent generator based on a random Fourier modes. It creates complex multi-scale velocity fields with eddies, currents, whirls, like smoke or cream in a coffee. The generator can control energy at different scales to get structured chaos.
That sounds expensive to simulate for millions of images.
That's why they use the lattice bottom method, a well-known approach in computational fluid dynamics. It performs local updates, ideal for GPUs.
The paper states that blur and noise behave differently in frequency space. Can you explain that?
Sure, if you look at the energy spectrum of an image, how much information is stored at each frequency, you see very different slopes. With Gaussian noise, as in DDPM, the spectrum gets fluided from the high frequencies downward. Noise at equal energy across scales, so fine details are overwhelmed first, then the coarse structures. On the other hand, with blur, the heat equation, the spectrum decays in a straight line on a log scale. The frequencies sink quickly, starting from the higher ones, but the slope is constant. By adding advection along the blur, this new method reshapes the spectrum. It both scrambles and blurs the details in the pixel space while still conserving mass, something that isotropic blur or noise alone can't do.
So, how do they control corruption consistently between images of different scales?
With two-dimensional numbers. First, the packlet number is the ratio of swirl to blur. It controls the advection term. When packet number is equal to 0, the forward corruption process reduces to pure blur. And the next one is the Fourier number. It sets the diffusion budget, so the total amount of blur.
Let's talk about the results. Did reversing the turbulence swirls improve generation?
Yes, On the FFHQ datasets, the quality in terms of the FID metric has improved from 55, so this is the baseline berm, to 36 in case of the moderate swirls. Although, these numbers are not as impressive as the state-of-the-art DDPM, the quality jump is massive compared to purely blurring baseline.
What about the diversity?
Higher packet numbers also increase the PFDC metric.
But too much swirl hurts.
Exactly. Too much chaos overharms the model. The sweet spot is a moderate swirl.
So, the big picture.
Embedding the turbulent advection in the blurry corruption process improved realism and diversity. It respects conservation laws and opens the door to mapping more physical laws, energy, entropy, space-time dynamics onto AI training.
Thank you for the conversation.
Thank you.